All right, and today we will have our first lecture in Chapter 5. It's Lecture 11, though of course the numbering of the lectures can change a little bit from time to time. Chapter 5, Lecture 1. And this is going to be your first lecture on the second law and on entropy. In this first lecture, we're going to give you a motivation as to why you need the second law of thermodynamics. We will formulate the second law of thermodynamics in a variety of different ways. There are alternative ways to formulate that second law. And we will introduce this mysterious concept of entropy. So let's first take a look at what the spontaneous thermodynamic process is. A spontaneous process is one whereby a system that starts out of equilibrium goes to thermodynamic equilibrium. Very simple examples. If you have a body here at a temperature above the temperature of the air around it, and you let it sit for a while, the body of heat, the hot body, will dissipate its heat to the neighboring air, and it will reach thermodynamic equilibrium when the temperature of the body and the temperature of the air are the same. I can do the same thing with a cylinder of pressurized air, for example, at a pressure P sub I that's higher than the atmospheric pressure of air outside. I punch a hole in the thing and the air escapes until the air inside the cylinder is at the same pressure as the air outside. That is a spontaneous process. There are others. I can take a mixture of two gases, say gas A in a certain number of moles Na, and gas B, certain amount of moles Nb in two different reservoirs with a partition between them. I break the partition, the gases mix with each other, and you have a mixture of gases Na and Nb. Another one is potential energy can become an inertial internal energy when the mass fell. So I can have a mass here, drop it, and now the potential that went into that has just translated into an additional internal energy in this block of mass. So the processes that reach toward equilibrium are spontaneously. Such things cannot happen in reverse. You cannot have a canister with a hole in and hope that the atmospheric gas somehow magically will increase the pressure inside the canister. This cannot happen in reverse. Now, you can reverse the initial state of the system, but not spontaneously. You have to do something to the external system to get it back to where it started. In other words, you have to use a pump to take atmospheric air and put it back in your canister and then seal it off. So let's take a little look at what that looks like formally. In the case where we had the outside air at a pressure P0 and an initial pressure Pi higher than P0, we punched a hole, and yes, we can take the pressure from the body and send it outside, and we can actually connect a little motor here or a little fan motor or something that will take the release of this air and make work out of it. So yes, you can deliver gas from the vessel to a little turbine. That makes work. Or not necessarily a little turbine. This can be big, and you can use a big turbine. Now the question is, can you take outside air and bring the system back to P sub I? Can you start from here and then get it back to where it started? The answer is yes. If you deliver work to a pump that takes this outside air, you can get the air to the inside the vessel back to P sub I, and you can restore the initial situation, but only at the expense of having spent work doing this. With temperature, it's a little bit more sophisticated. So you have a hot temperature that you let, you have the body at a hot temperature and you let it cool down spontaneously to the temperature of the outside to 0. Can you use that to make work? Well, yes, of course, you can use a heat engine, like we saw before, a thermodynamic cycle, thermodynamic power cycle. Use this temperature as the hot side temperature, use this temperature as the cold side temperature, and you can do work. Now, can we take a system that was initially at equilibrium and restore it to the initial temperature that was hotter? Can you do that? The answer is yes, you can do that. You can deliver work to a system undergoing a heat pump or a refrigeration cycle, but in this case, you would have to have a heat pump. Now, if you recall from when we had in lecture 4 the thermodynamic cycles, what thermodynamic cycles were doing is take heat from a hot body, put that in a system, which, by the way, in a PV diagram rotated clockwise. It would release heat to a cold side and emit work. So this is a power generation cycle. That power generation cycle is what we could have attached to this hot reservoir as hot side, cold source as cold side, and make work. But when we looked in lecture 4 at the refrigeration cycle, what we had is a system that takes in work, takes heat from the cold body, and sets that heat to the hot body. So this is a cycle that we would have needed to take a temperature initially at T0, at equilibrium temperature outside, and make it hotter by pumping heat into it with a heat pump. Now the heat pump will cost you work. All right, so let's summarize what we have seen so far. We could get from this initial situation, a pressurized canister, a hot body, to a final situation by a spontaneous transition where we let the gas out of the canister or we will let the hot body cool down to atmospheric, to ambient temperature. Now, as I showed you too, we can go back through another part of a thermodynamic cycle in this case, because this would be a cycle. But we do need to do something extra to get it back from final to initial. So typically you have to do work. Processes are reached toward equilibrium as spontaneous. Spontaneous processes cannot happen in reverse. I already said this. Yet both spontaneous processes and reverse processes are all allowed by the first principle. Now, the criterion that tells you if you have to do something more or if you can let it happen spontaneously, that is your new thermodynamic function. That is what we call entropy. In the very beginning of my class, I explained that heat was sort of disordered motion of atoms or molecules or particles of all kinds, whereas work was ordered motion. Well, so the degree of disorder is in fact the entropy. So that I'm not writing down because it's very subject to misinterpretation, but it's the most commonly understood, most popular version for the word entropy. We will stick to very formal definitions. So let's now get to the second principle, and the second principle has to address the following problems. First, we have to determine the direction of process, forward toward equilibrium or backward away from equilibrium. That is something that has to be determined by second principle. Second principle establishes a condition for equilibrium. This will make use of this variable entropy. And here is the formal definition of entropy by Enrico Fermi. Entropy is the thermodynamic variable that gets maximized as an isolated thermodynamic system tends toward equilibrium. That is formal. Now, what are we going to do with this? Well, we're going to also be able to determine the best case theoretical efficiency, best case theoretical performance of thermodynamic cycles, which would be what would be the maximum amount of work that can be produced in a power generation cycle, or what is the maximum value of the efficiency of the power generation cycle, the amount of work per amount of heat that you put in. And it will also determine what is the maximum amount of heat that can be pumped by a heat pumping cycle for a given amount of work that you put in. So this is now the coefficient of performance, as we saw in lecture 4. So entropy is a thing that will determine the factors that prevent us from reaching this maximum performance. It's also at the origin of the definition of the absolute scales, the Kelvin scale and the Rankine scale. It will also determine absolute scales for internal energy and as a corollary of the other thermodynamic potentials. For example, we saw the other potential, the only one we saw so far was enthalpy, but I mentioned to you in passing that there are others like Gibbs free energy and whatnot. So these formulations of the second law, which we haven't gotten to yet, like the first law, are postulates. They are based on measurements, they are based on observation. This law has never been violated. There are no exceptions. No matter what the system you're in, no matter how complicated the physical system you're in, this has not been, there have been no exceptions observed. All right, so the second law, of course, has quite a bit of history, and it can be formulated in a number of ways that are exactly equivalent to each other. We have the first, the oldest one, 1851 here, is by Lord Kelvin, William Thomson, the first Baron, Lord Kelvin. There we go. This was in Transactions to the Royal Society of Edinburgh. About the same time lived a guy in Switzerland at the ETH in Zurich. He was born in Pommern, which is northeast Germany, by the name of Rudolf Clausius. Looks quite serious. And we will go over these two formulations in a minute. One that I find very attractive, and is the one that I already gave you for entropy, comes from Enrico Fermi. It's a little booklet called Thermodynamics, Prentice Hall, 1937. It's been re-edited by Dover Editions, and you can actually find it if you wish to read that book. Here's Fermi. And let's go through the formulations themselves. So, the Clausius formulation will tell you that it is impossible for a system to operate in such a way that the sole result will be transfer of heat from a cooler body to an upper body, without doing to a hotter body, without doing any work. So you can have heat that spontaneously flows from hot to cold, but without doing any work, you cannot have heat that spontaneously flows from cold to hot. That sounds quite intuitive. Well, it is a formulation of the second law. It's almost common sense. The Planck formulation is far less intuitive. That's a Kelvin formulation. It was reformulated at the beginning of the 19th century, the 20th century by Max Planck. And Kelvin said that it is impossible for a thermodynamic cycle to deliver a net amount of work while receiving energy from only one single thermal reservoir. This energy is heat. So if you have one thermal reservoir here, and you put heat into a cycle, you cannot get work out of it. All you can do is heat up your cycle. But you cannot make it produce any work. This is forbidden. So, in other words, in order to be able to do work, you have to have both a hot source, a hot reservoir, a source of high temperature heat, and a source in which you can dump heat at a lower temperature. You have to have and a high temperature and a low temperature, hot and cold. This will work, this will not work. That is the Kelvin formulation. Now I have a great pleasure to demonstrate that the Clausius and the Kelvin formulations are equivalent. And we will do that by proving that if you violate Clausius, you will violate Kelvin. And if you violate Kelvin, you will violate Clausius. So let's do this. It's part of what I like to do, actually. It's not very practical, but it's fun. So let's get ourselves a system that violates the Clausius formulation. Imagine you have something here, and you can have heat flow from the cold reservoir through it into the hot reservoir. Now I need to show you that you can build a machine that would violate the Kelvin formulation. All right? So let's take this thing and let's add to it a power generation cycle here. So this would be my cold reservoir started from my hot reservoir. And now let's make ourselves a power generation cycle here that takes heat from the hot reservoir and puts it in the cold reservoir while doing work. Okay? Now that I have attached that, let's reframe it. Just change your control volume. So that now you look at these two machines as one. So consider the combined cycle as one single cycle. The next thing you do is you balance this QC that comes from this one here to the QC that goes up here. So this QC equals that QC. Remember, the signs of the QCs were opposite in generation cycles than they are classically. But okay, so you make that equals to that. If you make that equals to that, it means there's no heat that the combined cycle will dump into the coal reservoir. In other words, if this equals that, this net QC is 0, and your system looks, your combined cycle, looks like the Kelvin formulation, which is forbidden. I can reverse this completely. So if I find something that violates the Kelvin formulation, then I will also violate the Clausius formulation. So let's take this here. We take a hot reservoir, we take a cold reservoir, but we're not connecting our system to the cold reservoir. So here's my Kelvin violating machine. I could take heat from the hot reservoir and produce work. Let's assume we can do that. Then we add to it a refrigeration cycle. So now we have here a machine that takes in work and that thereby pumps QC into Q hot. Okay? Now, the next thing that I do is I reconsider my control volume to have a unified machine that combines these two cycles. So now this unified machine takes Q hot, does work, sends exactly the right amount of work into this machine to pump QC into Q hot. And what have I done now? I have made a cycle, this combined cycle, if this work equals that work, just gets heat from the cold side to the hot side, which is forbidden from the Clausius formulation. So that thing would amount to that thing. Of course, the heat I would pump up here would be Q prime minus QH, this one minus that, but still, it tells you that you can pump heat from cold to hot, which of course you know you can't. Well, wait a minute, you cannot pump it. Of course, you cannot have heat that spontaneously goes from cold to hot without adding work to it. That is a Clausius formulation. Now we get to the practical formulation, which is the entropy formulation or the Fermi formulation. So this starts from an isolated system that always approaches equilibrium spontaneously. The entropy, as I said before, is by definition the function that gets maximized as your isolated thermodynamic system tends toward equilibrium. So that means that the entropy of an isolated system cannot decrease. It always goes up toward its maximum during the spontaneous evolution of your system toward equilibrium. Spontaneous evolution is always toward equilibrium. So that does mean that the entropy of an isolated system can isolate it, means you don't do work to it. It can only increase as it comes to equilibrium, or if it is already at equilibrium, it will remain constant, but cannot decrease ever. Now, be very careful with this formulation. If the system is not isolated, entropy can be removed from the system by heat transfer. You can suck heat out of it and decrease its entropy. That is possible. So this definition always relies on the concept that the system be isolated, 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 isolated. But if it's not isolated, then we have to consider the transfer of entropy in and out of the system, as well as the part that's spontaneous from the isolated system. So we're doing this here. This is the rate of balance equation of entropy. Just like we had one for internal energy before, we do the same thing for entropy. So if you have a process, the change of entropy contained within the control volume with time in your process, let's call that delta S, that can be either positive or negative because it can be affected by the net amount of entropy transfers into or out of the system, into minus out of the system. And if you transfer more out of the system than into the system, then that number will be negative. Now, of course, since your system evolves, the amount of entropy produced by spontaneous irreversible evolutions inside your system, that we call sigma, whereas these we call S. Sigma, that is always positive. But this certainly isn't, and therefore this doesn't necessarily have to be positive. So heat or mass transfer can be sufficiently negative to make the total amount of entropy change become negative, but never this, and never, of course, the entropies themselves. Entropies themselves are defined positive. So that gets me to the entropy formulation of the second law, which is, it is impossible for a system to operate in ways that entropy is destroyed, is decreased. You can suck it out of your system, but you cannot destroy it. So entropy production is always greater than zero. This is entropy production. This is entropy change. Change is the result of either production or transfer in or out. Entropy production is always greater or equal to zero and never negative. When your system is ideal, it will actually be zero. In all practical processes, it will actually be positive. So I repeat, be very careful between the concept of entropy change and the concept of entropy production. Change can be negative, production is never negative. Entropy production is an indicator as to whether a process is possible or not. In other words, if you make a calculation and you end up with something there, it has an entropy production that's negative, that's not right. You know it's not possible. And so this actually, if that were possible, you would be able to build perpetual motion machines. They're called perpetual motion machines of the second kind. And almost by definition, the US Patent Office will refuse to patent any perpetual motion machine first or second kind. So this is because entropy production has to be positive, and negative entropy production means it's not possible. And then, of course, the magnitude of entropy production is a measure of the irreversibility of the system. We'll get back to that when we go through cycles and we use entropy in a practical way. So what are these irreversibilities in the system? A process is irreversible if the system and all parts of its surroundings cannot be exactly returned to their initial state after the process has taken place. So really, if you have a heat transfer through a finite temperature difference between two parts, and unless you do work on it, you will never be able to return that system to its situation. Expansion of gas, like we showed, a spontaneous chemical reaction, mixing, friction, of course. If you slide two solids, you make warm, you make heat. Well, if you take two solids and put heat, they're not going to start moving against each other. So this is an irreversible process. Viscous flow is, in fact, friction inside the molecules of the flow, so it has the same property. Classic one that you know very well is the little electric heater, where you pass current through a resistor. Well, if you heat up the resistor, you're not going to get your current back. So that is also, electrical resistance is a form of friction of electrons against the atoms in the resistor. Another one that you may be familiar with is plastic deformation of solids. If you take chewing gum and you pull on it and you put it on the table, it will not contract. It will contract a little bit, but it will not contract all the way back to where it started. So that is, again, actually a viscous flow or an irreversible process, formation of dislocations, which cannot be cured. So that's the end of this first lesson, and we will continue this in the next lesson on entropy. Thank you.